Log on, tune in, find out. Another good idea from Cambridge.
I'm with the Australian National University in Canberra, Australia. I want to thank the organisers for giving me the opportunity to give this talk here, and I should also recognise my co-authors on this work, Andrew Kingston, Glenn Myers and Adrian Shepherd. There's been a lot of other people involved in the work as well. Is this a laser pointer somewhere? No? In particular, there's been a lot of help from the workshop, from technicians, so to get this working. But essentially, I'll be talking about a development which started about maybe 3 years ago, where we had a journal club. We started reading papers, and one of the papers we came across was Katsevich's paper on theoretically exact reconstruction from 2002. And reading that, we thought this sounds really cool, so we decided to see if we could get it working. Just to put this in a little bit of a context, though it's been done before as well. In 2 dimensions, X-ray reconstruction is essentially the same as as inverting the radon transform. It was studied almost 100 years ago. Essentially, we get if we have parallel beam projections, we measure the projections at all different angles around the object, and we can get a simple reconstruction by just taking these projections, smearing them back through the object. That's what's called the back projection, and we get an image like that. Now, these kind of images aren't all that great, they're a little bit fuzzy, so therefore we introduce what is called a filtering step first, where we, instead of taking the projections, we apply a little bit of a filter to it, and then we smear it back, and that's filtered back projection. So that's how it works in 2 dimensions. In 3 dimensions, it's we should note that the X-ray transform is different from the what's referred to as the plane radon transform. X-ray transform gives us the integral of X-ray attenuation along straight lines. The radon transform is the integral of attenuation over 2-dimensional planes. So therefore, inverting the 3-dimensional radon transform does not help us. And it took quite a while before people were able to do full 3-dimensional reconstruction. Just want to point out a couple of papers here. Tui presented in '83 a result which tells us what sort of trajectories do you have a source, you have a detector, what sort of trajectories do you need for the source and the detector to follow around the object in order to expect to get a reconstruction. And essentially the criterion is that if you draw any plane through the object, all the planes that you can draw through the object must intersect the trajectory in a non-tangential and non-ended way, as he describes. Essentially, that means a helix is good because any plane you can draw through this object will cut through the helix. A circular trajectory is no good because we can think of a horizontal plane just above the trajectory line intersects the object, but not the trajectory. So therefore, X-ray data we measure along a circle is not sufficient for getting us an exact reconstruction. Nevertheless, in '84, Feldkamp et al. Came up with a very nice generalization of the 2-dimensional filter back projection into 3D cone beam for exactly this trajectory. And indeed, it's been very successful, and in micro CT it's almost been exclusively used, both because it's efficient to compute and it's very, very stable. Further along, in 97, we have a result which was used by Katsevich later to say that the helix, for a helix, we can show that if we have a source and a detector and any point inside an object which we can find here will be on one pi line, as he referred to it. That means that really to reconstruct the object somewhere here, all we in theory should need is the X-ray projections from this region. We shouldn't need all the information above and below. If we base any reconstruction on the three-dimensional radon transform, we would need all that kind of information. So that sets us up for the Katsevich reconstruction, which, as I said, came in 2002. It is composed of a shift invariant filter and a back projection step. So it's in a way it's and this shift invariant filter is along a set of cleverly chosen lines, one-dimensional of lines here. So you do one-dimensional filtering along each of these lines, and then you do back projection and do a couple of derivatives as well, and that gives you your reconstruction method. The proof is actually quite, the proof in this paper is quite elegant as well, which is sort of why we liked it. Cleverly show how contributions from these two parts cancel out and you get an exact reconstruction. Anyhow, enough about that. Micro CT is CT but for small objects. Typically we look at in our lab look at objects like this. This is a rock sample, and the aim of that is to get the geometry right, and then afterwards we perform fluid simulations or compute permeability, porosity, these sort of things. On these rock cores we analyze other samples as well, but we want to have a high resolution image which is geometrically faithful to this object. That in micro CT that's typically done with circular scans. Now with a circular scan, if you have a square detector, you can at most expect to get a cubic region reconstructed out of that. So in order to get a good image of this whole object, you would need to do a set of many circular scans. An alternative would be, of course, since you have a long object, you could do a helical scan, and there will be sort of one scan instead of many. That's not necessarily a very good reason. However, the other reason for why we want to consider this comes from the acquisition time. Micro CT, since we are aiming for high resolution, we need for the source to be very, very small. And well, we can see that because the size of the region where the X-rays stem from, that essentially limits the resolution of our object. If we consider an X-rays coming from one side of the source and grazing the object, and the other side of the source and grazing the object, we see those lines will cross there, and they will extend a region there, which is essentially the image of our source spot. So this needs to be as small as possible, otherwise that will be a limitation for our resolution in the image. Small spot size, that means we need to focus all our electrons onto a very small target, and generate X-rays there. Unfortunately, we don't only generate X-rays, we also generate masses and masses of heat. So that means there's a limit to how much energy we can focus onto the spot, and therefore we don't have that many X-rays. So signal to noise is a problem. These type of scans can take maybe 10 hours, 20 hours. So we need to utilize the X-rays better. One way to do that is to take the detector, which typically is far away, and move it much, much closer to the object, much closer to the source, and therefore we increase what we refer to as the cone angle. Now, cone angles, if we increase the cone angle, then we start with a circular scan, then we start to see the problems with a circular trajectory. The image in this central region is reasonably good. However, as we go up, we see these sort of streaking artifacts coming out from under these spheres. This is a simulated data set. And that's a result of the approximate nature of the filtered back projection Feldkamp method for a circular scan. If we instead use the theoretically exact helical reconstruction method, we see we're able to get all the circles nice and crisp all the way out. I think this is was about 30 degree cone angle simulation. So that shows why we want to use these sort of theoretically exact methods, is that we don't have a limitation on the cone angle. Typically for a circular scan, you're not recommended to go above sort of plus minus 5 degrees or something like that. People do use more, but really then you can expect to get problems with that. But these theoretically exact methods don't have those sort of issues. So that's all well and good. Once we worked that out, we went to the workshop and got them to build this nice machine for us. And a few months later, we have this one with the X-ray source, and here we see this flat panel. It's 40 by 30 centimeters. It's quite big. We typically run it at a distance of about 330 millimeters from the source. So we run it at quite a substantially larger angle than what we could with a circular scan. So we place the objects there and perform scanning. And then we were quite happy. This is one of the first images we took. We discount the obvious beam hardening. Then this image looks pretty good. We have, in this case, a 30 micron voxel size. However, when we start pushing the machine, things don't look quite as good anymore. This is a not 30 but 3 micron voxel size. And this should be a sandstone, and we see that these grains are not uniform, not quite shaped the way they should be. So something is going wrong. Okay. So the question is, what on earth are we doing wrong? There are a few things it could be. Of course, the inversion formula is continuous, derived in a continuous manner, so there are discretization issues. Now, there are several papers on how to implement this, and we're not really pushing any boundaries there, so that should not be an issue. And also, the artifacts we're seeing don't quite match what has been reported as discretization problems. So we didn't think it was that. Other thing, of course, we're working with real data here, so noise could be an issue, but the artifacts are not, they're not noise-like, so it's not that. Then, of course, we have the machine. The machine needs to be, we have to do the reconstruction, we make assumptions that everything is perfectly aligned, everything works around a perfect helix. And that's of course not true in a real world. In fact, we have at least 9 geometric alignment parameters. We have horizontal and vertical shifts of the detector, distance to the detector, distance to source, and 3 rotations of the detector, and also these axes may not be quite parallel. So there are quite a few alignment parameters that could be off. In addition to that, there are other issues as well. The source moves around. It's a function of time. It's never quite there. Yeah, quite a few things to deal with. So in order to look at that, we need at least to analyze these alignment parameters, we need some sort of consistent way of looking at the sensitivity of the reconstruction. And we decided to look at what we referred to as optimal units. Basically, what this means is that if we back project from the source to the detector, and if we change one of the parameters, for example, in this case the horizontal shift, by a given number, say 1 optimal unit, then that should correspond to the back projected ray through the object should not deviate more than roughly 1 voxel in the reconstructed image. Now what that means is that if we were to do nearest neighborhood interpolation in the predictions, then that sort of alignment would not matter. Now, we don't do nearest neighborhood interpolation, but if we were to do that, then it would be sort of okay. If things start to deviate more than 1 voxel in the reconstructed volume, then really we shouldn't be reconstructing at that resolution. We should bin it down by a factor of 2. So that gives us 1 optimal unit. And since we do that for all parameters, all the changes in any parameter will then give approximately the same sort of amount of error in the reconstructed volume. So if we shift the detector sideways, that's what we do here. So if we shift it sideways with 1 optimal unit, let's see. Just to illustrate what we're doing, if we have the source here and draw a detector through there, and so we have a length L, and then we have a detector width, so that's width on 2. And now the length there, we have this angle alpha f, it's a fan angle. So the length there is W on 2 cos alpha f. So that just tells us that the ratio of, if we move it by 1 optimal unit at the detector, then at the back here we should not deviate by more than 1 voxel in the reconstruction. That's all it is. The other parameters are a bit more involved. You need to invoke sine rules and cos rules, but it all boils down to trigonometry to find out what these sort of parameters, what these are. And if we insert a typical reconstruction geometry for our problem, we see that for the horizontal shift, we have about 0.13 millimeters. That's a little bit less than 1 detector voxel, 1 detector pixel size on the detector. Sample distance, on the other hand, we need to know to 2.6 microns. And that's quite tough. in particular since the that's the distance between the rotation axis and the spot inside the gun where the X-rays stem from. So that's not a distance we can measure physically. More to the point, it's a distance that can change over time. It changes as the filament in the source gets older, so this is hopeless to measure. The other ones are sort of okay, not too bad, but this is the really difficult one. I can mention that if we start with the X-ray source cold, turn it on, that distance changes with at least 40 microns. So let's just quickly look at a couple of, see what the sample distance misalignment look like. This is, we see, this is more or less aligned. This is off by 4 units, this is off by 8 units, and we see a more or less compression. If we subtract these images from the original, we see a compression type change in the reconstruction. If the detector is offset sideways, again aligned 4 and 8 optimal units offset. We see there, this is quite scary actually. This is an edge that's white, this is an edge that's black. So that means we have an object that's reconstructed and it's actually sheared. But these edges look okay. So if we didn't have the right reconstruction here, we couldn't really know whether this was in fact supposed to be like that or whether it's misaligned. So we try optimization-based reconstruction, essentially what they do in digital cameras. Look at the gradient of a reconstruction image and aligned, misaligned. And we search for over the parameter space, but that does not quite work as well as we would have hoped. This, the optimal parameters should be roughly there. It's peaked for detector offset, but certainly we don't have the right peak for sample distance. It's more peaked here. So something is not working the way we really want it to do. And we also see here why this sharpness measure doesn't quite do it for us. These edges are quite crisp, but so are these ones. And in fact, that's one of the problems we see with this reconstruction method, is that we are, by using the Tam-Danielson window in the predictions, we are avoiding the use of redundant data. So we don't have data conflicts, even though, or we don't have as much data conflicts as we would like. So even though we're back projecting with an incorrect geometry, we don't get as many, we don't get intersecting rays which sort of defocuses the image, so as much as we would have hoped. This is the Tam-Danielson window, the window of data which we back project for this method. So, recognizing that we need more data conflict, we use what we started to refer to as a fast filtered back projection. Fast because it's quick and dirty, it does not give any good images, it actually produces shocking images. I've referred to it here as Feldkamp with a twist. It's not quite Feldkamp either, because we don't account for the right weighting factors. We simply just apply horizontal ramp filtering on the data to and then back project without any weights. The trick here is that the ramp filter cleans up the edges a little bit for us, sufficient to get a bit of sharpness to them. The back projection still ensures that all the edges are back projected to the right location, assuming the geometry is right. If the geometry is off, edges go all over the place, and we now back project the full projection with full weight and therefore we get maximum inconsistency if the geometry is incorrect. So we can look at these images instead. This is what you saw previously with the Katsevich reconstruction. Nice crisp edges also when it's misaligned here. This is the quick and dirty reconstruction. We see these edges are nice and crisp. Magnitude is totally off, but that's not all that important. What we're interested in is the gradient of these images, and the slow variations don't really impact that much on that. So in this case we see that the edges start to defocus and these edges are completely blurred. That looks a lot more promising, and indeed if we start to plot these kind of plots, we see that instead of having this non-convincing surface which we need to find a maximum for, we have a very nice pronounced peak at the right location there. So this is of course, we can search for the optimal parameter set in various ways. And in fact, it turns out that these parameters decouple quite nicely. If we just search for them in the right order, we can do simple one-dimensional parameter searches and find a reasonably good approximation, and we can iterate that a couple of times and we are where we want to be. In addition to that, we don't need to reconstruct the full volume. We can only reconstruct a couple of slices and evaluate it on that, as long as we choose our slices right. So this is actually quite fast. It goes, it's just maybe 50 to 80% of the time it would take to do a full reconstruction. So this is an example of our image before alignment, and this is what it cleans up to once we've aligned it. Here again we can go back to a sample distance, misaligned, a bit better aligned, and in this case it's fully aligned. This is now at 3 micron voxel size again. This is a comparison example where we used a circular scan and compared it to the new scanning machinery. 11 hours acquisition time for a circular scan, and similar for the helical scan. We can see the signal to noise is just dramatically much better. This is one of our helical scans using this geometry. It's a 5mm sample, and if we used a single circular scan, this is the height we could reconstruct with this geometry, while staying within the 10 degrees cone angle restriction. This is reconstructed with 4 revolutions of data. So if you go through the numbers and find what sort of speed up you get, you can do a speed up of 10 times for maintaining the same signal to noise in the reconstruction, and therefore of course we can reconstruct much larger volumes. Yep, so instead of taking maybe 20 hours, we can now get decent images in 4 hours. Reconstruct much larger objects, obviously, essentially limited to disk space, how much we can, prediction data we can save. We have reconstructed down to 1.5 microns, but we're currently limited by the source. It's not performing quite the way we would expect it to. Thank you.
Perhaps we can take one question while we get the next speaker up.
So very quickly, I was just wondering, perhaps an actual thing to try would be to forward project the data that you didn't use in the reconstruction, and then use that as a fitting criteria for your unknown parameters. Did you try that? Or some reason you didn't do it?
Not explicitly, but I guess we're getting sort of that effect by blending everything in. But I suppose you're proposing to reconstruct with that and just only use that as a
reconstruct with Katsevich, and then look at the data that you didn't use in Katsevich, and then forward project your reconstruction, and then use the fit of that to tune your parameters for motion.
True. As long as you compare it with the data you did not use, that
Yeah,
could
so-
possibly work out. No, we didn't try that. Thank you.